In this video, we continue with an example that we did in a previous PinCast, where we wish to find the volume of the solid generated by revolving the region bounded by the x-axis, x equals 0, x equal 1, and y equal x squared plus 1, about the y-axis. So in the PinCast, we drew our region, we rotated it about the y-axis, we saw how it looked like a cylinder with a bowl cut out of the top, and then we went through a fairly complicated, not too bad, but fairly complicated way of finding the volume of that solid. Now what we wish to do in this video is to use a different method, a method called the shell method that will help us to find that volume in a somewhat easier way. Now, in order to do this, we're going to use a video of the shell method for this particular example that's on mathDemos.com, I believe is the website, or mathdemos.org. So, let's look at the video. It is mathdemos.org. So first we have our region that we're going to revolve. But instead of slicing this horizontally, as we did when we looked at the PinCast, we're going to slice this vertically. And then when we take one of those regions and we rotate that about the y-axis, you see that that gives something that looks like a shell, a cylindrical shell, or like a short piece of pipe. Now, each then of these regions, where we've got our rectangles that we are approximating with, we'll just go halfway around here so you can see half of these shells as we go around and how that builds up the solid. But of course then that was only half, so we'll go ahead and put the other half in. So these shells then approximate our solid. Now again, what does that solid look like? One way we can do that is to take that region, and again we'll show rotating it around so that it will look like that cylinder with a bowl cut out of the top. Now this video is going to continue looping around as I explain what we'll be doing in order to try to find the volumes of these shells. So the idea is, for each shell that we have, we'll have to find its volume. So we'll have to find, say, the volume of that shell as it is rotated about that axis. So how will we do that? Well, we have to have something that's like a shell, and here I have the air filter out of my 91 Chevy S10 pickup, an old-fashioned pickup with a carburetor, and the idea is to show you that a shell, and this is a shell just like the ones we have there in the video, can be made by looking, or we can find the volume by looking at the volume of a box. Now what do we mean? Well, when this was made, well, the molded plastic pieces on top and bottom were made as circles, but this part in here, the inner part, was not made necessarily as that shape, that circle. What you could do is you could cut this apart. I don't want to cut it because I need to put it back in my truck when I'm done with this demo. But if you cut it apart and laid it out flat, what would it look like? It would look like a box where you would have, so again, think of cutting this and laying that all out flat. You would have a height here, you would have a length there, and you would have that width this way. So you would have all three of those dimensions in a box, and you would find its volume by multiplying those dimensions. So let's see if we can figure out what those dimensions would have to be. So look at the diagram. Do you see the height of the shell? The height of each shell happens to be the height of the curve, right? So that would be our height, and then the thickness of the shell is our delta x that we've been using to slice with. So we know again, when we have our region here and we have that rectangle and we rotate that rectangle around to get our shell, that the shell height is the height of the curve. which in this case is x squared plus 1. Y equal x squared plus 1 was the equation of that curve. And then we said that the shell thickness was delta x. But what about the shell radius? The shell radius of the shell, is the distance from the y-axis to the rectangle where we're at, but that's our value of x. So that shell radius then is x. So we have our shell height, thickness, and radius. Those are the three dimensions of our shell. Again, height of the curve, our dx, and then our radius are the three things we need. But how do we find that volume then? Again, let's think about cutting this and laying it out flat. The shell height is one of these dimensions of the box, and so is that shell thickness. That would be that distance as you are laying this out. So the shell height goes forward and backward. The shell thickness goes up and down. What about left and right? Well, if you cut this and lay it out, it would be the circumference we have here, right? Would be the length of that box. That circumference would be pi times, or 2 pi times the radius, right? 2 pi r is the circumference of a circle. So again, our volume then becomes the three dimensions of the shell height times the shell thickness times the shell circumference, which we said was 2 pi times the shell radius. But that's just one shell. And as you can see, there are many shells that make up our approximation. So we have to add all those up to get our approximation. And of course, it's a fairly rough approximation, but if we want something that's nice and smooth like this approximation as we're rotating it around, then what we would need to do is take the limit of these as we go to infinitely many. Or in the infinitesimal system, look at the infinite sum, where we have infinitely many rectangles in an infinitesimal width. So therefore we get that infinite Riemann sum, or that limit of Riemann sums, and once more, it's a definite integral. And everyone rejoiced. Everyone should say, woohoo! Yahoo! It's a definite integral, because it's a limit of Riemann sums, or an infinite Riemann sum. So we get then the integral from left to right, a to b, of, if we want a formula then for the volume, what would it be? The delta x becomes the dx. You have a 2 pi times the shell radius times then the shell height. So our formula is 2 pi shell radius, there's shell radius, shell height, and then the shell thickness goes away into your dx. So those are the things we'll need to know. Now, in our case then, and let me back up over here, and I'll go ahead and erase the diagram since we have a better diagram now in our picture on the internet. So we've got what? The integral from 0 to 1, because it was from x equals 0 to x equals 1, of 2 pi times x squared plus 1 dx. And if you continue, you'll get, of course, 3/2 pi cubic units for your answer.